let me see here. Let's do that. Oops. Let me share my screen really quick, and then we can get started. Share. Okay, we're gonna get rid of that. All right, here we go. All right, so here's the schedule for the week. Make sure you have your calculator out, something to write with, and some paper. So we had a quiz yesterday. I graded it. The first thing we're going to do is go over it today. Then we're going to do the week 2 overview. So just going over all the content for this week. And then we're going to review definite integrals just because you're going to need that for improper integrals and for area of a polar region. And then we're going to go over the practice final exam problems. Since I did cut some of the stuff that wasn't in the curriculum, we're going to be done with the new content today. So Wednesday will just be office hours. So if you do want to meet for office hours on Wednesday, just let me know. Please note that office hours are not meant to be for learning. It's meant to be for if you need to like review something or you're not understanding. It's for like clarification purposes. I'm not going to be going over an entire 2-hour lesson or anything like that. It's just to answer questions. So it will not be a lesson per se. It'll be more about just clarifying certain things, working out problems with you, that sort of thing. So it's not going to be a long process. It's probably like 15 to 20 minutes if you want to meet for office hours. Completely up to you. Yeah. All right, next. This was the quiz. There was 3 different versions of it, so there's 3 different problems. So if you notice right here, there's different problem here, here, and here for 1A, and then same with B. Actually, I think I changed the numbering around a bit, but either way, there's 3 for each section. So when we go over the answers, make sure you follow along with whichever section you were on. The first one is 9 a.m. The second one was 1 p.m. and then the third one was 5 p.m. So you should know which one you were on for the time for the quiz. So let's probably go over the quiz now because I'm sure that's what everyone wants to see. Where did I want to go with this? Hold on 1 second. Let's quit out of this. I'm going to open it up in a separate thing here. Quiz 1. All right. And it did not open it up. Hold on 1 second. That's embarrassing. There it is. All right, so number 1 is right here. I'm going to try to just zoom in here on number 1. All right, so this first one here, so pardon the noise. This first one here is first one. So this is the 9 a.m., this is the 1 p.m., and this is the 5 p.m. It does that order each time. Take a look at it. The main things I was looking for, feel free to ask any questions too if you got them. The main things I was looking for was, do you have each of your primes correct? And then did you divide them to get the actual derivative for each of them? Okay. That was for 1A. Let's do this. Okay, yeah. Next thing I was looking for was, did you set the derivative equal to 0 or undefined for each of them? To solve, here's all the answers. I will be posting these answers as well, so you don't have to worry about watching the video to get these answers. I'll actually post the solution guide for it so you can kind of see the work in more detail. Is there any questions on number 1 for any of the times? Nobody has questions? All right. Number 2 is over here. First thing I was looking for here was, actually, this is wrong. I forgot to change that for my last class. It doesn't matter. The answer's still right. This is still 0. Things I was looking for was, did you have your R prime when you plugged in whatever angle it was? Was that correct? And then did you actually set up the derivative equation correctly for each of them? Questions on any of those? Again, the 9 a.m. is up here, and then 1 and then 5. No questions? Okay. Number 2A was right here. It was all of this part right here. Let's get rid of this. Oops. Okay, things I was looking for on this one was making sure you pick the right U for each of them, because if you did that wrong, then the problem is almost insolvable. You had to use integration by parts. If you thought it was U substitution, that would not work. Questions on 2A? All right, and then there's 2B right there with each of the times. I guess I should have gone over how I grade first, so this makes a little bit more sense. So I'm gonna write this over here. So the way it works is every problem is gonna have a grade A, B, C, D, or F. I usually don't write F. I'll write like a question mark because I just don't know what's going on. An A is if you have 100% everything correct. It's neat. You showed work. It's a bad W. You showed work. Everything that it's readable. The main thing is the showing the work part. That's the easiest way that people don't get A's. In real life, like your boss, your teacher, whoever. Actually, I shouldn't say your teacher, but in real life, your boss doesn't actually know the answer to whatever problem you're working on. Say you're an engineer and you're trying to engineer or design something. You have to kind of figure out what the best possible path is, and you have to like neatly show work and explain your reasoning behind why some certain project you're working on is the best way to go. Your boss isn't going to just look at it and go, oh, that's correct, because there is no right answer for that. So it is really important to neatly communicate what you're working on. So that's why it's an A. Even if you got the right answer, if you didn't show work, you're not going to get full credit. A B is if you did like a minor algebra error. Okay, so anything that was not covered in this class, so previous math classes, like algebra classes, not calculus, that's what a B would be. So your calculus was all correct. It's just that you forgot a negative number, or you forgot, I don't know, I can't think of anything. It's just like to distribute correctly, you forgot to add something wrong. Like it's a minor algebra error. A C is if you do multiple minor algebra errors. So if you do multiple of B's, or as long as you have one minor calc error. So say you forgot the plus C, then you automatically go to a grade of a C. Okay. A D is if you have multiple minor calc errors or a major calc error. Okay. If you have multiple minors, it's kind of a major calc error. An F is if you just didn't really do anything. You just showed me no evidence of any learning or pretty much anything. Okay. Now, the reason I do it this way, there's no points attached to any of this, is because points don't actually make sense. You're probably used to points because that's what you've been taught with the entire time is, oh, this problem's worth 5 points. This problem's worth 3 points, that sort of thing. The problem is points are just completely arbitrary. They don't really mean anything. It probably means something to your professor, like in their head it means something, but it's not like 1 point means you learned one thing or anything like that. It's not a unit of learning. It's just an arbitrary thing. I'd rather grade it based on a rubric, which is what this is. It's graded based on what kind of error you did, which means all the problems have equal weights for the for how much like they're worth. There's not one problem worth more than another, that sort of thing. Here, let me delete this. I'll go on to help you figure out how you actually get your quiz grade. So the way it works is if you got, okay, so there was number one, there was an A, a B, and a C for this. You have an overall grade for this first problem, and then you have an overall grade for the second problem. And the sub problems like the A, B, and C give you your grade for the overall for whatever you did for number one. So for example, if you got an A, and a B, your number one grade is just going to be an A. Okay, and I do a 100% A, even though this is not 100%, you would still get an A for this one. Okay, and then so say for number two, you got a B on the first one and a C here. A B and a C would be a B, so you'd get a B for this one. And then overall, an A and a B for these two problems would give you a grade of an A overall. Okay, I don't really average it out. I just try to meet in the middle as much as possible. If I did average it out, it would pretty much be the same thing here. But that's just kind of how it works. That being said, if you do get an F on a problem, it's just kind of a grade killer because you showed me absolutely nothing. Like if you worked a job and you knew absolutely nothing about something that you should know about, you would probably get fired. So I do take Fs as very serious. Like you would get no credit for that, and it would lower your overall grade highly. So say you actually got, like, instead of a B here, you got an F. Like you would probably just end up with a D here, just because this would just kill your grade. Obviously, this F wouldn't be from these grades here. Now, granted, this doesn't usually happen. It's not like you get an A on one section and you completely bomb the other. I mean, it does happen, but it's very rare. But that's basically how I do grading. That being said, all grades are negotiable. So if you feel like I was grading you too harshly on something, then you can email me and I'll take a look at it, or you can talk to me after class about it, whatever you want to do. And we can figure out what a more fair option is for you for that grade. Are there any questions on how I do grading? Okay, the reason I do the A, B, C, D the way I do is, here's how some professors might do a problem. You end up, say a problem is like worth 3 points, and you forgot to do a negative, you forgot to put a negative number in it. It was supposed to be like negative x squared plus c or something like that. But say you forgot this right here, you might lose 1 point on that. If you lose 1 point on that, you are now dropped to a 2 out of 3, which is a 67%. So you just missed one little thing and you got a D. Okay, where here you would still end up with a B for that problem. That's kind of why I don't do points. They're so arbitrary. They don't really make much sense. I believe that professors have like the best intentions of it, but it doesn't really, to me, it's just not fair. Okay, everything is equal weights. Everything has a certain grade to it. And then a specific section has a section grade. That way, if you do bomb a section, the other one can still help you. It'll make more sense as we go, but if you notice your quiz grade, your quiz file that I sent you, that picture, it'll say your initials, and then it says Q1, that's just quiz 1, and then it's going to say your grade. This is your grade overall in that quiz. Okay. Any questions on the quiz? Any specific problem that people need to see? Again, I will be posting this. I just haven't done it yet.
I had a question for the last, overall question on the quiz.
The third one of the last one, or which section?
I had the 1 p.m. time.
Oh, okay, so middle.
It's not, doesn't matter for my grade, but for my final answer, I took 3/10 out and then used parentheses. Would that still technically be correct? Or can I not distribute with that?
You factored, so you factored out a 3/10 like this,
yeah,
and then did this, and I marked it wrong?
Yeah, well, you just put an arrow indicating that the 3/10 should have been there. It was kind of an unnecessary step I took, I realized, but.
Well, I don't care if you distribute or not, because that's just algebra. I shouldn't have taken any points off for that. So
yeah.
Can you email me and then I will fix that? I'm sorry.
Yeah, no problem. I just want to make sure that I did it right.
Yeah, I mean, I would pull up your test, but then everyone's going to see it, so I don't want to.
Yeah, it's fine.
Do that. Yeah. Yeah, I'm pretty quick on fixing grades too. So if you do have any mistakes, please, anybody, let me know. Email me, whatever. But I don't care about that kind of stuff. Like that's, yeah, I hate professors that think that that's important. It's not. Like whatever you want to do. If it's right, it's right. That's the way I look at it. So anybody else? Okay, I am going to close this then. I'm going to do a little, where am I at here? I'm going to do a little preview of the rest of the lesson today, and then we'll get going on this. So here was the test, all the problems. So Unit 4, so this is just going to be integration. The only thing that was from Unit 2 was that polar and parametric differentiation. The rest of it's pretty much integration from here on out. We do a little bit of stuff with derivatives, though, in Unit 6, but it's not like a derivative unit. But anyway, integration. It's all about antiderivatives. The main goal of calculus with integration was to find the area of any shape, not just squares, circles, rectangles, but what about some weirdly shaped objects? Now, why is this important? Because whenever we want machines to make things, just think 3D printers, that sort of thing, you need to, code them, and computers only understand math. So to be able to make some weirdly shaped object, you have to explain it with math, and that's the whole importance of this. I'm assuming that's why engineers have to take this class, but I really don't know. But area of a plane, so it's the area of any shape, including non-basic shapes like this one. But today we're going to be working on stuff that, what about a shape like this? Okay, so this intersects at 0 here, but what if I wanted to find the area from 0 to infinity here? Okay, so this graph right here is getting infinitesimally closer down here. Does that mean it's getting infinitesimally closer, but it's also getting infinitesimally longer, like the width of it is getting further and further out there? Does that mean that there's an infinite area? Does it converge to an area? We don't know. Maybe somebody knows, but we're going to be going over that today. What about a graph that looks like this? Okay, now we have, say we're finding the area from this value right here to this value right here. Is it infinity because it goes up forever, but they're both getting infinitesimally closer? I don't know. We're going to have to figure that out as well. And then we have this one right here where now it goes infinitely up, but infinitely closer to the y-axis, and then the same thing only with the x-axis. It's going infinitely to the right, but getting infinitesimally closer to that x-axis. Does that have an infinite area, or does that converge on a value? So that's kind of the main idea for today. But before we go over that, I want to review Riemann sums. You do not need to write this down. You should know this from Calc 1. Riemann sums is basically the geometric way of thinking about integration. Until we go to infinity, which would use limits. That's the calculus part. So Riemann sums here. This first, just look at these 3 pictures right here. You're basically, I'm trying to find the area underneath this curve right here, but I'm trying to do it by approximating with rectangles. So you can draw rectangles underneath here to kind of approximate. And if you notice, this first one represents one rectangle, although it has no height, so it's just a line. And it's bounded by the left upper corner of the rectangle. So if you can see, the rectangle goes up and stops right away because it knocks into that graph. Okay, it's not very exciting. The area of 0 here, obviously the area isn't going to be 0 because you can see that it's greater than 0. It's this positive value here. So let's look at this next one. Now we have 2 rectangles, even though this is still just a line. But you have a rectangle here and a rectangle here. If you notice, it's filling in more of this area here. Here it was filling in none of it, but it's filling in more of it. So it's a better approximation. Then if you use 4 rectangles, this third one right here, if you use 4 of them, you're filling in even more of that empty space. Whoops, sorry about that. So as you can see, the approximation is getting closer and closer to the area underneath. So theoretically, how many rectangles do you need to get the exact area? Anybody? Does anybody remember this?
Infinite, right?
Infinitely many. Okay, and then also, what is the width of those infinitely many rectangles? If you notice, the width here is 2, the width here is 1, the width here is 1/2 for each of these. What's the width of all those rectangles if there's infinitely many?
Should reach to 0, right?
Yeah, it's approaching 0, exactly. So if you have infinitely many rectangles, they have to be infinitely thin to fill in the area completely. Otherwise, it's going to be off by a little bit. Okay, this is left Riemann sums. You're never going to need to do this for this class, but it should be a review from previous content. Okay, here we have one where it's bounded by the right upper corner. So if you see right here, we have a rectangle, but it's bounded by the top. So the rectangle goes up until the upper right corner hits the graph. So we have 1 rectangle here. Here we have 2. If you notice the upper right of each of these rectangles, it stops. Here we have 4. If you notice, these are going to be overestimates, but it's the same principle comes into play where the more and more rectangles you use, the more and more exact your area is. Okay, so these are going to get you the same answer if you use infinitely many. There's another thing that you had to learn before, was midpoints. Now you're doing the rectangle that's bounded by the middle of the rectangle up until the graph. So if you see this first one here, it stops in the middle. This one stops in the middle here, and then this one stops in the middle, and then all 4 stop in the middle here. This is the midpoint Riemann sum. This is even more exact. If you notice, there's less white space, but there's also a little bit of an overestimate here too, so it's kind of actually hard to tell that one. Okay, and then the last one you should have learned about was the trapezoid rule, where if you add more and more trapezoids, it starts filling in the space more and more. Now, if you notice, this is a triangle here, which is basically a trapezoid with one of the base lengths to be 0. You can think of it that way as a triangle. But as long as if you could see that if you add more and more of the trapezoids, it fills more and more of the area in. Again, infinitely many, yielding the exact area. Okay, I made some graphs. I mean, that's how I did all these screenshots here, was I made a Desmos file that shows this, and I think this is pretty neat, but I'm very biased probably with this. All right, so we have that x squared from 0 to 2. So if you notice right here, it says x squared from a to b, 0 to 2. And I only have 2 rectangles here, okay? So what I can do is I can add more rectangles here. And if you notice, it starts filling in more and more and more each time. You can still see the white space, but I'm going to fill it. I'm going to go right to 100. If you notice, it looks like it's filled in all the way, but you can zoom in here and see, there's more. So what I'm going to do here is add more rectangles. Okay, now it looks like it fills in more, but if you zoom in, still see some more. Okay, I'm going to do it again. Still see some more. Okay, and you can just keep doing that. Eventually, if you zoom in enough, and if Desmos didn't run out of memory, you'll see that it's still off by a little bit. Okay, but it's a pretty good estimate for what we're doing. Okay, so hold on 1 second. Let's do this. Okay, so let me zoom out real quick. I do have, we are comparing this to the exact area is found using definite integrals. This should be a review as well. I wrote it in right here. Let me zoom in here. I wrote it in right here. So the exact area, this thing right here, should be 2.6 repeating. Okay. Now you might go, why is it repeating? Why isn't it actually doing like the fraction? You can make it a fraction here, but what this computer is actually doing is just counting infinitesimally small things. I mean, it still has a finite value, but it is very, very, very tiny. But your computer's just rounding it off, basically. This computer's just rounding it off. Your calculator does the same thing. It's not actually doing the antiderivative and plugging things in. It's simply just counting, and the calculator can count faster than we can. Here is it's basically summing up the area of all of those rectangles here. And if you notice, this is an approximation, this 2.28, and this 2.6 repeating is the exact. But watch what happens if I increase the number of rectangles. So let's do 100 here. If you notice, this 2.6268 gets closer to this 2.66. Now, if I just overload this thing, you notice it starts getting even closer to this value, okay? You don't need antiderivatives to do this. You just need to add up a bunch of rectangles. Now, this would obviously take us a long time. To a computer, it's absolutely nothing. Okay, the same thing happens if I change the C value. It goes to, I guess I should show let's do this. Let's do this. So if I change the C value to 0.5, it does the midpoint for all of these. Again, you can see the same thing. It converges to that area underneath. And then if you do the right-hand sum, it does the same thing, converges to all those values. Okay. Also, if you notice right here, if you add more and more, it still gets closer to that exact area here. Okay. Hopefully this is ringing some bells for people. I also made a trapezoid rule program. And if you notice, if you add more and more trapezoids, here, let's zoom in here. Let's do no trapezoids. And then if you start adding 1, 2, 3, 4, you just keep adding them up. It's going to fill it in exactly to get the exact. I don't think I actually wrote that in here, though. It's okay. It doesn't matter. All right. So that's trapezoidal and Riemann sums. That should be a quick review of that. Again, I'm not going to actually ask you any of that, but it does come in handy later on for the class. Here is I coded this in Python, if anyone knows what the Python programming language is. And basically, it finds the right sum, left sum, midpoint sum, and trapezoid sum based on the number of rectangles or trapezoids based down here. And I went to 100 again. And if you notice, they start really far away. And if you remember, the exact value is 2.6 repeating, which is oddly where all of them converge. It's not odd. That's meant to happen. If something is integrable, I don't know if I'm saying that right, but if it has an integral, then this will happen every single time. They will all converge. If it doesn't, then that means it probably goes to infinity or negative infinity. It diverges. It's not integrable. I feel like I'm saying that wrong, but that's okay. So if you notice, they all go to the same value. So that's Riemann sums. Here is something that you've seen before, but basically, if you add up infinitely many, this is adding up. This sum notation is adding up the length. The height times the base, or length times the width. You can do it that way. If you add up infinitely many rectangles, you get the integral from a to b, the definite integral from a to b of the function. And you don't need to know any of this. Again, it just should be a little review for you. Is there any questions on Riemann sums? Okay. Okay, 432 is all about the fundamental theorem of calculus. We're not really going to go over this too much in this class. We mostly focus on the first fundamental theorem, which is what definite integrals are all about. If you do want to find the exact area, all you have to do is take the antiderivative, that's what this capital F is, plug in B, plug in A, and then subtract the two values. Okay, so if I was going to do that for the problem that I was just on, that I was just doing, so say I was doing the don't write this down. I just want your brains for right now. If I was going to do this problem, what you would do is you would do the antiderivative. That's the antiderivative of that. And then we're integrating it from 0 to 2. So we're finding the area from 0 to 2, like I was just talking about a second ago. Okay, and then if you do that, you have to plug in 2 to this, and you get 8. You plug in 0 to this, you get 0. And you end up with 8/3, which is that 2.6 repeating. If you notice, I didn't have to add all those things up like the computer did. Okay, but it's the exact same principle. Okay, one involves adding things up. The other one just finds the exact by using the antiderivative. Okay, again, this should all be a review. Here is the graph just to kind of review this stuff. You can't have negative area. So if I move this over right here, if you notice, there's more red than blue. So I just programmed this to change color basically. And if you notice, the area here is negative. It's the capital F of B minus capital F of A here, and it ends up being negative. If I added more positive here, now this becomes positive. Okay. You can go back this way. I don't know, it's pretty cool. That's the first fundamental theorem of calculus. You are going to need that. I'm going to need this later. You are going to need that for definite integrals. We're not going to cover the second fundamental theorem, if you remember that. It's tons of fun, but we're not going to worry about that for this class. It's beyond the scope. Okay, definite integrals, again, it's the same thing as the first fundamental theorem. So it's what I did here. This is definite integrals. You should know how to do that. We are going to review today how to do that, but you should know ahead of time. The new things we're going to go over would be improper integrals. And these are things that involve limits going to infinity. So limits are needed for finding the infinitely many rectangles that are infinitely thin. But what if you used limits on the endpoints of the integral? So we had this is 2 right here. What if I got rid of this and put infinity? Right? That means you would have to change this to probably b here, and then we're doing the limit as b goes to infinity, and then what do you end up getting? Well, you would end up with infinity, if you can see, because if you plug b in, b to the third, if b is going to infinity, you would have an infinite area if you went to infinity on this. It's not that exciting. If you went to the graph, you could see that yourself too. So if I did x squared, you could see if I did the area from 0 to infinity, it's going to go to infinity. I mean, I'm not even going to infinity, and look at how huge this number is here. Okay, so you can kind of get an idea of how that looks with improper. That would be one case of improper. Another case would be is if you have a vertical asymptote. So this infinitely many, it usually deals with horizontal. This usually deals with vertical asymptotes. I'm going to show you an example of that later. Actually, I already showed you an example in the very beginning. Come on. This one right here. Okay. It's vertically going to infinity, even though horizontally it's not, because I stopped at these points here. So we're going to do those problems today. Those are fun. And last thing we're going to go over is the area of a polar region. So there's only really 2 things we're covering today. So that's why we're going to change tomorrow to an office hours day. The area of a polar region, I can't actually make a Desmos file out of this because it doesn't fill the area correctly. But you know, polar regions are generally circular in nature. And you can see right here, if we have this, it's not actually a circle, but you have this curve right here, this polar curve. And if you just added up the slices of pizza, if you want to like break it down into pizza slices, if you add those up and you added them up infinitely, if you added infinitely many of them that are infinitely thin, you would get this formula right here. Okay, it's all based on the sector formula, the area of a sector formula, which is 1/2 r squared times theta for radians. Okay, now if you added up those areas, okay, that's what turns into an integral. So the area, the added up area, the total area would be equal to 1/2 r squared d theta, because it's the infinitely thin thetas. If you go back to this picture, infinitely thin thetas times 1/2 r, which comes from the sector equation. If you do not like this explanation, I made a video that was way more in depth of where this equation comes from. It's on my website right here. If you scroll down, hopefully this is on mute. Nope, it's not. That's embarrassing. All right, but I actually go through the entire like breakdown of where everything comes from, and I draw a bunch of like slices of pizza and stuff like that, and show where the equation comes from. I don't actually draw pizza; it just looks like a pizza. So if you're interested in where that equation comes from, it's there. But again, beyond the scope of the class, so you don't really need to know where this equation comes from. You are going to need to know how to use it, though. Okay, so that's basically a sneak preview of everything we're going to cover today. If it's way over your head, hopefully it'll make more sense when we do a bunch of examples, and hopefully you start thinking about questions that you want to ask during this whole thing, because yeah, it's pretty involved. Any questions before we begin the lesson section here? So let's save this. Okay, week 2. All right, so I didn't really go over the statistics from the quiz, but there was mostly A's. So it's 10 A's, 7 B's, 3 C's, 5 D's, 2 F's. The average, if you actually did average this out, it was an 80, but it's just a B because I don't really do points or anything like that. But if you did like count an A as 100 and a B as an 80, 70, 60, and then an F as, I think I count them as 50, it averages out to about a B. But not a bad spread. Hopefully people fix their issues that they have with anything they got wrong. Next thing I want to do, so there's 4 things we're coming over. The quiz here, the quiz 1, we already did that. The reviewing definite integrals, improper integrals, and area of a polar region. And then I also put 2 problems from the fake final on here so that we can go over those. So yeah, let's go over definite integrals really quick. Okay. So what I would want you to do right now is take about 2 minutes and start number 1. I will put a timer on, and once that's done, we will go over how to do that problem. If you do have questions during these 2 minutes, please ask. Otherwise, I'm going to slowly start doing the problem. These are, oops, why did I do that? That's embarrassing. These are old school problems, so you should know how to do it. None of this is new, so this should all just be review for right now. Why did I do that? I didn't even copy the problem right. Here we go. Okay. Okay, again, if you have questions, just chime in. Step 1, find antiderivative. Okay, the next step, we have about 20 seconds. You plug in 2 pi. And then you subtract off when you plug in pi. Okay, and that's time. Okay, does anybody want to help me out here? What's cosine of 2 pi?
1.
So that ends up being -1, right? Very good. And then this ends up being plus cosine of pi, which is what? -1. So your final answer should be -2. Did anyone else get that? Okay.
Yes.
Cool. All right. So what I'm going to do here is go back to this Desmos file I made. And we are going from pi 2 pi. So we're going to have to zoom in here. If you notice, it is negative. So we did get -2. And if you actually look at this graph right here, -2. Okay, also, I'm going to show you how to do this on your calculator so you know how to check it. So pull your calculator out. You probably already know how to do this, but just in case you forgot, this definitely helps. So we're going to clear all this out. Math 9 is your friend. Okay, so you're going to hit Math 9. I'm in polar. I'm going to change that to be in function really quick. There we go. Quit. All right, so Math 9. Okay, we're going from pi to 2 pi. And we're doing sine x with respect to x. Hit enter, and you end up with -2. So when you're allowed to use your calculator on the quiz, I would highly, highly advise doing the problem with your calculator first and then start working it out and see if you get that same answer. Or if you want, do it by hand and then check on your calculator. It doesn't really matter the order. Any questions? All right, cool. Let's try the next one, which is going to be trickier. We're going further down the rabbit hole here with each of these problems. So it's the integral from 0 to 1 of x cubed over the square root of x to the 4th plus 9. I think, actually, with respect to x. Let me just check really quick. Yes. Okay. Okay, this one I'm going to give a little bit more time on. So let's do 3 minutes. What integration technique should we use for this? Anybody? Someone chime in, please.
U sub.
U sub. Okay. Now, how did you know that you should use U substitution? It doesn't have to be late. Yeah, go ahead, Laith.
Because when you take the derivative of x to the 4 plus 9 will be x cubed. And you know you can substitute it out.
Boom. So your U right here, when you do so he said your U is x to the 4th plus 9. When you do this derivative, it shows up right here. Well, part of it does, the x to the 3rd. So that's a good sign. Thank you for explaining that. Okay, try working it out. If you get stuck, ask a question. Got about 2 minutes. Okay, this x to the 3rd dx is equal to du over 4. So I'm going to substitute that in over here. And then it's 1 over the square root of u. So that's going to be u to the -1 power. Okay. Here's a little shortcut for you, too. I highly advise doing this. Plug in 0. Now, this 0 is in terms of x, but we're in terms of u now. So what you can do is take this 0 and plug it in, because it's x. Plug it in here and you'll be in terms of u. So it's going to be 0 plus 9. This turns into 9. Okay, you can do the same thing with the 1. Plug it in over here. You get 1 to the 4th plus 9 is 10. So now you don't have to go back to x. Usually you have to substitute your x back in, but you can just keep everything in terms of u, which is going to be a way easier set of numbers to work with here. So I'm going to pull the 1/4 out. You got about 10 seconds. All right, I pulled the 1/4 out. For this right here, you have to add 1 to the power. Then you have to divide by that power. And then we're still going to integrate it from 9 to 10. Any questions so far? this all simplifies to be, this is 1/2 on the bottom. So it's the same thing. Dividing by 1/2 is the same as multiplying by 2. Multiply by the reciprocal. I'm going to put that up here. And then you have u to the 1/2. And we're integrating this from 9 to 10. Again, you do not need to substitute the u back in to be in terms of x. We can just stay here. So you're going to end up with 1/2. And then it's 10 to the 1/2 power minus 9 to the 1/2 power is 3. And you get your final answer there. If you prefer square root signs instead of to the 1/2 power, by all means, go crazy. Doesn't matter. It only matters if you have a professor that cares about that stuff, but it's easier just to do 1/2 power, in my opinion. All for programming anyway. Okay. Any questions on the work I just showed? Cool. Let's go to the calculator. So we're going to do math 9 from 0 to 1. Okay, we do have a fraction. So here's a little tip. If you don't know how to do the fraction bar in your calculator, hit alpha y equals, and then it says n over d, that's numerator over denominator. Hit enter on that, and now it makes a little fraction for you. So you can put x to the 3rd here, and then x to the 4th plus 9, excuse me, dx. Hit enter. Okay, did I do that right? Nope, I forgot the square root. That's embarrassing. 0. Come on, Lath. Are you going to help me out or what?
Not bad.
What do I pay you for? I do not pay him.
You pay me 1 cent per hour.
There you go. There we go. Now we're cooking with gas here. Dx. Hopefully you guys did it right. There we go. Okay. Now you should be able to test this. Obviously, this does not help you at all. But if you could test it with doing the 1/2 times 10 to the 1/2 minus 3, and it equals the same thing. So you know you did it right. Questions on any of this? There are no questions. I guess you've seen this before. This should be a review. All right. The other two problems I'm going to save for later if there's extra time and people want to do them. It's here's a little hint. For this one, you need integration by parts. Still another definite integral problem. And then this last one, you need to do integration using partial fractions. Okay, but I will save those for later because the other stuff we're going to go over is complicated, and I want to make sure everyone's brain is still fresh for those. Now, make sure you know how to do all of these because sometimes you'll have an improper integral that involves integration by parts or integration using partial fractions. You have to know everything. Everything in this class, everything in every math class snowballs. It all builds up over and over and over again. So make sure you understand the stuff from before. If you were like, cool, I got through week 1, I barely passed, but we're on to new stuff. You still have to know the stuff from week 1 for week 2, unfortunately. Okay, so we can do C and D later, but I now want to start with improper integrals. In this case, if I had this equation, y equals e to the negative x over 2, what is the area in the first quadrant? Okay, I don't actually give you an integral on this, so we need to create an integral. Does anybody have any ideas how to do that? Should I just like force people to talk? No, that's rude. I shouldn't do that. Steven, you don't got anything for me? Any ideas? Nobody? All right. So the area in quadrant 1 is going to be equal to, okay, we're going to start at 0 because quadrant 1 starts at 0 for x. And then it goes forever this way. So we are integrating from 0 to infinity for this. So it's going to be something like this. Questions on that? Now, technically speaking, you cannot have an integral with an infinity up here. Don't ask me why. I did not make up the notation. Math's a language. Certain symbols mean certain things. You can't have certain things in certain places. So you would have to rewrite this to be like this. Oops, I was going to square that for some reason. So you have something like this. Okay, questions on this? Cool. All right. Same rules apply. This limit, I'm just going to write this out here. Same rules apply, though, when you do the antiderivative. You have to do the antiderivative first, plug in b, plug in 0. So that's what I'm going to do. The antiderivative for this, e to the x, is the derivative is itself. So I'm just going to rewrite itself like that. And then you have to divide, because there's an inner function up here. You have to divide by that. When it's linear like that, you can just divide by whatever the derivative is. If you don't understand how I got this -1/2, just do the derivative of this, and you'll see that you get back up to here. If you want, you could also do u substitution, but it takes a while, so I would not do u substitution. Okay. And we are integrating this from 0 to b. b is going to infinity. Is everyone good with the red, orange, and green? I should ask first, does anybody think this is going to be an infinite area? Because it goes forever, but it's never actually approaching it? Does anybody think that? Yeah. Who said yeah? Lath? Okay.
Yeah.
Anyone else? This is not intuitive. Like, you can't possibly know this. And I already know that if you think you know it, I'm already going to trick you on the next problem we're going to do too. So none of this is intuitive. I mean, it's not like looking at it and go, oh, that makes sense. You have to actually like break down this math like we're doing. So let's just keep doing that. So one person says yes, and then everyone else said nothing.
Wait, I have a question.
Go.
Why are we taking the limit again? I'm very confused on the limit thing. Wouldn't it be the same if you just made b infinity?
Whoever made this, I think it was Leibniz, that's how you say it. Leibniz, he's one of the fathers of calculus. He just made it as a rule that you can't have infinity up there. Like there's no reason. Like it's a human decided that. It's not like the universe said that's impossible to do. It's kind of like why you have to capitalize the first letter of a sentence. Like math's a language just like English is. There's certain rules. That's what you have to apply. Am I going to care if you do it or not? No, I don't care. You're going to notice that I do it sometimes. Okay, you're going to notice books do it sometimes. You're going to notice that internet videos do it sometimes. It's a language thing. It's the syntax, if you want to think of it that way. Like a programming language has certain syntax. Like this is just how it is.
Yeah, I got you. Thank you.
Yeah, it is what it is. It's just so everyone's speaking the same thing. Like everyone, I don't even know. It doesn't. I feel like this says the exact same thing, so what's the point? If this was an infinity, it wouldn't change anything. I think part of it is when Leibniz first made limits, the only way you can get to infinity is using a limit because there was no like notation for infinity. So you had to use the limit. I don't know. I'm just guessing. It's not important. All right, so what I'm going to do here is this -1/2. Since you're dividing by -1/2, I'm just going to multiply by -2 just so it's easier math to do. All right, so you can plug b in here, and you're going to end up with -2e to the -b over 2. Okay, so that's plugging the b in. Then you have to plug the 0 in. When you plug the 0 in, you have to subtract this -2e to the 0. I'm not going to do -0 divided by 2 because -0 divided by 2 is 0. Okay. Is everyone still on board? I don't know why I ask when no one answers. This is, okay, I'm just going to assume. E to the 0 is 1, because anything to the 0 power is 1 except for 0. But, yeah, so that's 1. All right, now we need to figure out this limit here. So to figure this out, I'm going to rewrite it. This is going to get crazy. So negative 2 divided by, I'm going to make that negative exponent positive so I can put it on the bottom. Okay. Plus 2, because this negative becomes becomes a positive. All right. From here, we are going to infinity. So you have e to the infinity over 2. E to the infinity over 2 is just infinity. You can't actually write this down, but I'm going to do it anyway because it's just illustrative. If you have negative 2 divided by infinity, where does this approach?
0.
0. Okay. If you think about it, if you had negative 2 pizzas and you divided it by infinitely many people, you have 0. Okay. Even if you had 1 billion pizzas and you divided it by infinitely many people, you get 0 because infinity is always going to win. Okay. So that means, hold on. That means this whole thing is 0. This whole limit right here is 0 plus 2, which means your area in that first quadrant is 2, which means your area of something that goes infinitely forever to the right, never approaching 0, does eventually hit a limit, and that limit is 2. So if you could go to infinity, which we can't, it would be 2. So if you're thinking that's impossible if it goes forever, you're just adding more and more areas. That is true, but we're doing the math, and the math makes it possible because infinity works in our brains. It obviously isn't real, but questions on that? If you know 2? Yes, 2.
What?
I know. It's not intuitive. Awesome about it. Here, check this out. Let's do this. Let's do e to the, oh, wait till you see the next thing, dude. That's nothing. So we're going to do 0 here. If you want to see what this graph looks like. If you notice, if you zoom in enough, it's going to take a little bit. Give me a second. It does not reach it. Okay. You can't actually equal 0 on this function. It's impossible. If you try to set this equal to 0 and solve, it will not work. Why am I doing this? Zoom. Okay, there we go. Now, b is going to 2 pi right now because that was the last problem. Okay, so we're looking at this thing right here. This supposedly is going to be getting closer and closer to 2 if I go to infinity. So let's do 10. Let's do 100. Whoa, it already, okay, that wasn't exciting. That went to 2 right away. Okay, because it ran out of memory. Here, let's do this. So if you just do, this is embarrassing here. Okay, let's just do 2 here. If you change this, you can see that it's getting infinitesimally closer and closer to 2. We're looking at this right here, by the way. You notice it's getting infinitesimally closer to 2. Eventually, it caps out so early at 51. Wow. But that's just because it's exponential. Exponential grows really quickly. But anyway, you can see it goes to 2, even though it technically goes forever. And this can never equal 0. That will never happen.
That's so weird.
In case you care, in case anyone's like wondering why doesn't it not equal 0, here, let me show you. So if you did e to the negative x over 2 is equal to 0, think about it this way. Some power, this is 2.71828, whatever. Let's just say it's 3. 3 to some power could never be 0. Like what power could you raise this to get 0? If you raise it to negative infinity, it would, but negative infinity is not a real number, right? So that's why this can never be equal to 0. It's approaching it forever. But if you have an exponential and it's positive, it can never, well, it has to be positive if it's exponential. It'll never reach 0. Long story short, you have a horizontal asymptote there. But that's crazy. That is crazy. Okay, this is going to be a huge deep dive with vertical asymptotes this time. Or, hold on. Is there any, I don't even know why I ask. Is there any questions? I'm so used to the classroom where I ask this. Is everyone good with this? You will be given a problem similar to this. If you look at your fake final exam problem right here, looks like we got some U sub or something in there. Uh-oh. We're going to infinity. It's improper. So you should make sure you know how to do a problem like this. All right, let's go over this one. 1 over x to the p. Okay, p, let's just say p is greater than 0. Now, the reason I'm saying p is greater than 0 is because if it wasn't, that means it would be negative. And if this is negative, like say it was x to the negative 1 over x to the negative 1, that's just equal to x. Okay. If you have 0 to 1 for the area of x, that's very easy. I'm actually trying to do something that involves asymptotes, and this does not have an asymptote. So p is going to be greater than 0 for these problems that I'm about to do. It could be other values for different things, but for this example, it's going to be greater than 0. Okay, what I want to do is figure out what this integral is if p is greater than 0. This is very abstract. We're going to be staying in p. We're not going to be putting a number in for p right away anyway. And this is just insane. So that's kind of why I want to do it. Okay, ignore this graph for right now. It's going to make sense in a little bit. So let's just go down here and we'll go back up eventually. Try to write this down, pay attention, ask questions. I'm going too fast, so I'm going to go, whoa, 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 what did you do there? You went too fast. Okay, let's do this first. Okay, does anybody notice a problem with this integral right now as it's looking from 0 to 1, saying what's the area from 0 to 1 under 1 over x to the p if p is greater than 0? Why is that a problem?
Because you can't take the derivative of two variables.
Okay, you're right about that, but just act like p is 3 then. So you are right, but what else? Anything with that 0 seem a little bit weird? Someone has to know this. If we're doing the area from 0 to 1, can you put 0 into this formula?
Oh, yeah, because you can't, because it's going to be 1 over 0.
Exactly, to be divided by 0. 1 is being divided by 0, and you can't do that. Thank you, Matthew, for writing that in there. Yes, very good. So what we are going to do is we're going to get infinitesimally closer to 0, but not actually being equal to 0, okay? And to do that, you're going to need one-sided limits. What side do we want? The left side or the right side for this? We're going from 0 to 1.
Right side, of course.
Right side. So this is going to be a plus, okay? And we're integrating this from a to 1. Now, if you wrote 0 plus here, I've never actually seen that. I've seen infinity in there, but I've never actually seen a 0 with a little positive sign up there before. So that's another thing where they always use limits. Okay, so we end up with something like this. All right, let's see here. All right. Let's keep going with this. Now, we do reach a dead end because if you wanted, let's just keep going with it. Forget the dead end. Technically, we did hit a dead end, but someone will call me on it later, I'm sure, which is good. All right, so this is technically equal to, here, let's not put an equal sign there. This is technically equal to x to the negative p. Okay, so if we were going to do the antiderivative of that, what would it be? Well, you would add 1 to the power, and then you would divide by that same power. I'm going to put the 1 in front. I should have flip-flopped that. I don't like the way it looks, but that's okay. And we're still going from a to 1. Okay, so I just did reverse power rule. I figured someone would call me on this because I said p is greater than 0. So if p is greater than 0, what if p was equal to 1? Would we be able to do reverse power rule if p was equal to 1?
No.
No, because it would be ln x. So I figured, but we're going to get to that in a little bit. So just bear with me on this. And actually, this is so cool. All right, let's follow our definite integral rules on this. So what we're going to do is we're going to plug in 1 and we're going to plug in a, and we're going to subtract those two values. So first thing we're going to do is plug in 1 for x. So you're going to end up with 1 to the 1 minus p power over 1 minus p. Okay. Minus, now you have to plug a in. Let me put parentheses here. You plug a in for x, and you're going to end up with this. Something like that. Okay. Hopefully everyone's still on board. Now, if A is going to 0, what is this whole value going to be equal to here?
0.
0. So you technically don't need this limit anymore now because there is no more A's in this problem if this is 0. And you end up with 1 over 1 minus P. But if you remember from before, this is where it gets crazy. P is greater than 0. And I said before, well, if P was equal to 1, you would have to have ln x. Could P equal 1 for this purple equation here? This purple expression? No, because you'd be dividing by 0, right? So this works. This equation works right here is if P is greater than 0, but P cannot be equal to 1. Okay. But there's another but on this. There's so many issues with this. It's awesome. What if this is crazy? Here we go. What if P was equal to 2? So then you're going to have 1 over 1 minus 2, which is equal to -1. Why is this not right? Why is -1 not right for the area from 0 to 1 of 1 over x squared?
Because it's not a negative area.
It's not negative, okay? If you graphed 1 over x squared, which I believe the 1 over x squared here in this case is the red, it's clearly a positive area from 0 to 1. Okay, here's 1 right here. The area would be this thing right here. That's clearly positive. So this does not work for anything that's P is greater than 1. So it has to be less than 1. So long story short, this will only work if P is, between 0 and 1. So then what happens if P is equal to 2? Well, let's try to solve that one out. By the way, what I have graphed up here, it's kind of a spoiler, but what I have graphed up here, this green one is when P is equal to, here, let's color code this. P is equal to 1/2 for that one. The red one, P is equal to 2, and the blue one, P is equal to 1. Okay, so what we're going to do, if you notice, they all, from 0 to 1, they all have a vertical asymptote at 0. You can't divide by 0. But we're trying to figure out this area from 1. Trying to figure out all the way. What's that?
Can you backtrack real quick? How did you
Yeah.
get the purple again at the end? 1 over 1 minus P. Wouldn't it be 1 to the 1 minus P over 1 minus P?
Well, what's 1 to any power, Kebab?
Oh, just.
And remember, P is greater than 0.
Yeah.
So say P was 1 or P was 3 or P was 1,000,000. 1 minus 1,000,000, if you do 1 to the negative 1,000,000 power, it's still going to be 1. Sorry, I kind of sidestepped that real quick. Yeah, 1 to any power is 1. Okay. This is insane.
Yeah.
Okay. Now let's do one where P is equal to 2 and just see what happens. Okay, this should be very, very easy problem to do. So now if P is equal to 2, you're going to have x to the -2 from 0 to 1 dx. Okay. From here, you're going to have -x to the -1, and we're integrating that from 0 to 1. You can't plug 0 in here. So we're going to turn this into an a, and then it's the limit as a approaches 0 from the right. Okay. So you plug 1 in there, you end up with -1. Okay, you plug a in there. Now a needs the limit, so I'm going to write the limit in here. As a approaches 0, and you're going to end up with -a to the -1. Simplify that a little bit. -1 plus the limit as a approaches 0 from the right of 1 over a. Does anybody know that limit? You should know that from Calc 1. What's the answer for that limit? This limit right here in blue.
Is it 0?
You have one pizza and you're dividing it by some tiny, actually forget the pizza because it doesn't make sense. But you're taking 1 and you're dividing it by a very, 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 very small number.
Oh, infinite.
Infinity. Okay, you should know that, again, from the previous class. Well, infinity minus 1 is still infinity. So if you change p is equal to 2, for this up here, p is equal to 2, the area approaches infinity. For 1/2, whoops, I should do this in green. For 1/2, it should be 1 over 1 minus p. P is 1/2, so it's 1 over 1/2. So it's 2. So if p is 1/2, the green, it comes out to a value. If it's, I should have done that in red. If it's 2, the area is approaching infinity. Why would it pick 1 to be that way versus the other? Why is 2 any different than 1/2? Huh. Weird. What's going to happen with 1 then? Anybody know? Of course not. Let's do it.
It's between 2 and infinity, so it'd be a large number or some sort of number.
Well, no, the blue, it's not between 2 and infinity because, oh, I see what you're doing because, yeah, I get what you're saying. Okay, I thought you meant from the graph. Gotcha. All right, well, let's do it. It's not going to take very long. So we have 1 over x because p is equal to 1 for this one. So now we have ln, oops. Actually, you don't need the absolute values, but absolute value bars, but I'll do it anyway, from 0 to 1. Okay, ln of 1 is 0. So you're going to have ln of 1 minus ln of 0. You can't do ln of 0, but you can get infinitesimally closer to that. You might need your calculator for that one. Don't need the absolute value bars. But anyway, this ends up being 0. This, if you graph it, oops. No, I want to do that. All right, let's do that. So if you graph this, let's see here, f of x equal to ln of x. Oops. You notice as you get closer to 0 from the right, it goes down to negative infinity. Now, it's never actually reaching it if you zoom in enough. This is going to take forever. Oh, no. I think I scrolled down too far. I'm not giving up yet. There it is. Whew. It took forever. Okay, it's still not reaching it, but it's going down forever as you approach it from the right. So that's negative infinity, long story short. So you're subtracting off negative infinity. That's embarrassing. There we go. Subtracting off negative infinity, which is equal to infinity. Okay, so let's go back up here. T was equal to 1, the area goes to infinity. P is equal to 2, the area goes to infinity. But if P is equal to 1/2, it's 2. Even though all the graphs, all 3 of the graphs, are approaching the y-axis the exact same way. It's a vertical asymptote the exact same way. Why is this happening? We will go over this in Unit 6, actually, in great detail of why this is happening. It's actually, it's not intuitive at all, but it's still pretty interesting. Okay, long story short, that's what you do for when there is a vertical asymptote. I just thought it was cool to show it with different 1 over x's. Some people assume that it's infinity because it goes forever. It really depends on the function. Okay, depends on the function. Okay, I am going to take a 5-minute break here, or you can take a 5-minute break. I'm just going to sit here. If anyone has any questions or anything else related to this, just let me know, and I'll set a timer right now. Set timer for 5 minutes.
Your timer is set for 5 minutes.
Okay. You were confused on a step or something, please let me know. Lath's mad. No, I'm actually talking to Lath because he's like rubbing his head in the video, so I'm just giving him crap. Don't try to make sense of it. It doesn't make sense. You have to trust the math. It'll make sense when I show you this proof later.
I have literally no clue anymore. What?
Well, I mean, I can show you, oops, my mute. No, I'm not. I can show you one thing that's pretty interesting, Lath, that you might like. It's kind of beyond the scope of the class, but if you, this right here is where one of the problems, or one of the issues I should say is, if P, this P right here is 2, now you have A to a negative power because it's going to be 1 minus 2. And if 0 if 0 is going to a negative power, then that becomes infinity right there. So P has to be greater, I'm sorry, P has to be less than 1 in order for this to even work. Otherwise, you're dividing by 0.
Yeah. But in the end.
So that's part of the reason why you end up with a negative area if you do 2, even though it's not negative. But then if you actually work the problem out, you still get to infinity, is because when I was doing this problem, I was taking that into account already. It just makes it look like it's, I don't know, it makes it more intriguing, I guess, to look at it that way.
Very intriguing.
Yeah. It's very, very, very complicated. But as long as you know how to do the math for it, that's what matters. Just don't assume that, oh, it's 1 over x to the third. That means it's going to be infinity. Don't assume
Is
that.
it like a famous example problem?
No, actually, what we're going to do later on is more famous. It's called P series. If you want to look into it, it's really super interesting. With P series, though, it's going to infinity.
Yeah.
It's related to Taylor series, yes. It's going to be in the same unit. Taylor series is just the best. You're going to love Taylor series. You are going to love it.
Sheesh.
Yeah, Taylor series is basically, imagine turning a non-algebraic function, let's just say e to the x, f of x equals e to the x. Imagine turning that into a polynomial. Now that polynomial its derivative has to be itself too, because e to the x's derivative is itself. So what does that polynomial look like?
What?
Yeah.
Polynomial. What?
Oh yeah. Well, I know, dude. Believe me, I know. It's insane. I've known about this thing for like 20 years, and I still think it's insane.
You know what? I'm gonna make up my own math language.
There's actually an XKCD about that. Hold on. What is it? XKCD making up a new protocol. I don't know if that's what it's going to be. Is it this one? That's not it. Standards, maybe? No, dang it. Hold on. So funny because it's so true. No, it's not that one. Man, it's such a good one. Here, I'll just. This. Oops, that's time. Ah, man, I'll find it. It's so good. Does anybody like follow XKCD on this? Oh wait, I think I just saw one that was. Oh yeah, here we go. No, it's not it. Oh yeah, here. This is it. This is it right here. This is a good one. How standards proliferate. Okay, so situation, there's 14 competing standards. Like the standard of like, it doesn't matter, whatever standard you want to do. Like let's just do HDMI versus VGA versus like standard for what they use for like connections of a TV. Just that sort of thing. There's 14 competing standards. 14, ridiculous. We need to develop one universal standard that covers everyone's soon situation. There's 15 competing standards. So if you can, create a new program or math language, people are going to say, why do we have these programming languages? There's these math languages. I'm going to create another one.
Yeah, but it adds on to the problem.
I thought there's many programming languages too. I mean, among other reasons. All right, so let's go here. Okay, so that's basically all of 434. Okay, improper integrals, vertical asymptote, horizontal asymptote, interesting things happen. Let's go to area of a polar region. These right here are basically just, this right here is, we're gonna need this later on, but it's trig identities that you've probably long forgotten from pre-calc, so that's what that is. This is the area formula that we're gonna use. This is that animation, or not animation, that graphic I showed you before. This is a formula we're going to need, though. All right, let's see here. I want to pick a certain problem. Ooh, this is a good one. Okay. I want to figure out the area. Zoom in here. I want to figure out the area of this polar curve right here. I want to figure out the area from 0 to 2 pi. Okay, so before we do this, I want to look at a graphic of this, just a graph to see what it looks like, and let's make sense of it. Okay, so we are going to go, actually, let's do it on our actual calculators because Desmos doesn't really do polar graphs very well. Okay, go to your calculator, change it to polar, y equals, and we are going to do 2 times 1 plus, I think it was cosine theta. Okay, zoom 6, that doesn't matter. You end up with some graph that looks like this. Okay, now imagine finding the area of this. To find the area of this, essentially what we're doing here, let me screenshot this. Essentially what we would be doing, so pixelated, is finding, let's see, we're going from 0 is going to be 4, so it starts here. It doesn't matter. Imagine making slices of pizza. This is so, I'm sorry the lines are not straight at all. Completely around and adding up all these slices, but imagine these slices are infinitely thin. So that one's too thick. These all have to be infinitely thinner, and you're going all the way around. I hope you get the idea because this is so annoying. Oh, man.
Like a brain.
So I just went over the exact same one. All right, so you're adding up every single one of those when you use this equation up here. Okay, and if you're adding up every single one of those, then you essentially found the area of the entire thing. Long story short. Okay. So let's do it. So here we go. First thing I'm going to do is the equation, you need r squared. So right away, I always just find r squared because otherwise you have to rewrite a bunch of stuff. It'll make more sense as we go. Let's just find r squared first. And I would also expand this out as much as humanly possible because it makes the integral easier. So that's what I'm going to do. 4 times 1 plus 2 cosine theta plus cosine squared theta. There we go. Is there any questions on how I got this? This is all algebra. You've done no calculus yet. Okay, anytime you have a squared, you want to get rid of it. Okay, the reason why is you can't take the antiderivative when it's cosine squared. That's why I have this right here, these two equations. Okay, what we're going to do is we're going to replace that cosine squared with this thing right here. If you want to know where this comes from, I would Google it. It's very, very involved proof. You've seen it before because it was in pre-calc, but it's such a long time ago. It's not worth it. You don't need to know where the proof comes from, but we do need to use it. Okay, so I'm going to rewrite this. Oops, just distribute this. I don't know what I'm doing. 4 plus 8 cosine theta plus 4 times cosine 2 theta plus 1 over 2. I will give you these two formulas too, because what's the point? You can just write them in your calculator and memorize them that way. So I just rather give them to you. Okay, we're going to simplify this again as much as humanly possible. Okay, now we are ready to do the integral. We're going to use this formula right here. From alpha to beta, that's 0 to 2 pi. Here we go. So we're going to do the integral from 0 to 2 pi of 1/2 times this whole mess right here. So 4 plus 8 cosine theta plus 2 cosine 2 theta plus 2 d theta. So everyone's still on board. Oh, man. Okay. Okay, I'm going to simplify some things here. This and this becomes 6. Okay. Which is equal to 0 to theta. Okay, now I'm going to distribute everything out here. So you're going to end up with 3 plus 4 cosine theta plus cosine 2 theta. All of this is with respect to theta, and I wrote x for some reason. So, okay, now we need to take the antiderivative of this, hence the reason why we reviewed it from before. You're going to end up with 3 theta plus 4 sine theta plus sine 2 theta, divide by that inner derivative for 2, and then we're going from 0 to 2 pi. Now, try not to get intimidated by this. It's actually not that bad. If you plug in 2 pi here to that, it's gone. If you plug it into here, you get 4 pi, which is 0 still. So sine of 2 pi, 0. Sine of 4 pi, still 0. If you plug 0 in, you get 0 here and 0 here, and actually 0 here. So you end up with, if you plug 2 pi in, you're going to get 3 times 2 pi minus 0 times 3, which ends up being 6 pi. Questions on that? All right, I'm going to show you how to do this on your calculator now. Pay attention. Here we go. So we're going to do math 9 again. We're going from 0 to 2 pi of 2 times 1 plus cosine theta squared theta, and you get some crazy number. But guess what happens if you divide this by pi? You get 6. So it's 6 pi, just like we got here. And that's basically today's lesson. If you want to stick around and do the practice final with me, the 2 problems that are on the practice final, by all means. Otherwise, I will see you unless you set up an office hours time with me tomorrow. Otherwise, I'll see you on Monday for the quiz. Quiz is going to be 2 problems. There's going to be an improper integral problem and a area of the polar region problem. Questions? Is anyone going to stick around?
I'm going to. Can you hear me?
What's that?
Can you hear me?
Yeah, I can hear you. You're going to stick around? You want to do practice
Yeah,
problems?
I'll stick around.
All right, cool. All right, awesome. All right, let me save this. Okay, let's start with number 6. Kind of gave this away already, but what integration technique are we going to use?
Isn't it by parts?
Try it by parts. I don't think it's going to work, but try it. No, it won't work. It won't work because think about it. This is going to be your U. If that's your V, I mean, I'm sorry. If this is your dV, what's your V? You can't do that antiderivative. It's impossible.
Yeah.
So you need U substitution. Well, we'll try working it out. First person that gets the answer, let me know. I don't want to step on your toes. Oh, man. Oh, excuse me. Did you get a lot done? Because she was here. Like, was it good that she was here?
Oh, yeah. And it's a good, she was saying it's a good transition. Because, you know, she's gonna be here a full day and like, we're transitioning him and he also has to get used to her because, you know, he just has a
I didn't use the mic, but I'm giving Karis. Oh, buddy. Well, a good amount of people are still here, actually. That's good. All right. How are we doing? Does anybody need help?
Something to the infinity is just infinity, right?
What is the something?
E.
Yes. I'm going to graph this really quick just to see what it looks like. Hopefully people wrote it down already. I graph it on Desmos because it's better. Let's see here. Xe to the negative x, whoops, squared. Holy moly, look at this thing. Okay. And B, oh, B's at the 127. Did I write that correctly? Yeah, I did. Huh. Kind of gives away the answer. But that's okay. Oh, wait, this isn't the answer because it's at 1. There we go. Holy cow, look at that thing. Sweet. Sweet. Oh, jeez. Does anybody have an answer?
It's just infinity, right? Or
What's e to the negative infinity?
oh. Wait, how did you get it to be negative infinity? Wasn't it infinite positive?
Remember, you can change the u's. I'm sorry, the x values to be in terms of u.
You have to do that?
I would. Yeah, this is all in terms of u, so these have to be in terms of u. Plug 1 in here, you get 1 squared negative 1. Plug infinity in here, you get negative infinity squared, which is negative infinity.
Gotcha.
Yeah. Tricky. But only if you get tricked. Definitely stick around. I'm going to show you how to do this on your calculator as well. It's not going to give you the exact value, but you could test if your exact value is correct or not.
It's so odd how they have you do the notation with the limit instead of just putting it up there.
Oh, I know. You have to rewrite it every time. It's so stupid.
Does it come in handy later, like in a different, like later calc?
I don't think so. Honestly, I really don't think so. I can't remember if it did. I haven't seen Calc 3 in like 19 years. So no, it is very annoying. If you do not do it, I will not get upset.
Okay.
So, although I shouldn't say that because I am being recorded, but I don't think they're going to ever watch any of these, the college. But all right, I'm going to show you how to do this on a calculator really quick. So first thing I'm going to do is go back to the function regular. All right, and then I'm going to go math 9. Now we are going from 1 to infinity. I'm just going to put 100 in there for now. Okay, just because I want to. I'll do 1,000 next, but we're just going to look for that trend. X, so negative x squared up here with respect to x. Okay. It's going to take, oh, it didn't take as long as I thought. Okay. And then I'm going to hit second entry, and then I'm going to change that 100 to 1,000. Because remember, we're going to infinity, so I'm just going to see a trend. Oops, 0, 0. Hit enter. Oh, darn it. That definitely is not right. I think this overloaded it. Darn it. That's not good. Anyway, if you do 1 divided by 2e, you end up with that first value, which is the right answer. I think this just overloaded. Anything with exponential usually overloads it, especially since you're squaring what your exponent is, so it gets really huge, and it just starts truncating values because of the memory getting overloaded. Imagine it this way. This is a terrible analogy, but I kind of love it for some reason. But like, you can count with your fingers, but you only have 10, so you'd run out. Imagine like a computer's basically running out of fingers to count with. That's what essentially happened here. This is the right answer because I tested it on Desmos. It's the only reason I know that. Here, let me Right here on Desmos, I went to 127, but if you notice right here, it's just gonna, Desmos doesn't overload as fast as your calculator does, so I can put in, what is this, 1 million, 10 million, 10 million. But it ends up being that 1 over 2e. So this is actually how your calculator calculates things. It does it to 1 million, trillion, whatever, and then it stops. So, any questions on that? I don't know how to like protect against that happening. Oh, yes, I do. I just thought of something. Cool. All right, so this is what we're gonna do. Instead of starting at 100, let's start at 10. Don't start at 1 because going from 1 to 1 is just going to be 0, obviously. Oh, man. Okay, hold on. Delete. Okay, so 1 to 10. Always start at 10. That's the rule of thumb. Okay, if you start at 10, now go to 100. If the number stays the same, don't go any higher. See, then you know it's probably the value. Okay, so it stayed the exact same. So 1 over 2e.
Do 500. Without
All right. Why don't you relax a little bit, man? Just kidding. Yeah, dude. Whatever you want, do 500. Maybe it won't overload it, but I don't know. I just like foolproof ways of doing things. I mean, Lathe, we've talked about that before. Like I got a perfect score on the ACT because I checked every one of my problems with the calculator. So I made sure that everything was 100% correct because the calculator is basically your answer key. You know, I can think of a couple examples where it's not, but for the most part, you can use your calculator to check all your work. It's perfect. And it's not cheating.
Mm-hmm.
All right, how are we doing? Are we good with this problem? Can we go to the next one?
Yeah.
Yes.
All right, cool. All right, the first one right here, this limison, we're not going to do that one. We're going to do the second one here. Okay, the reason why is because it's more like indicative. It's a harder problem. So this other one was kind of like the same problem we just did. And I want to do something different.
I know in trig we used to like memorize the names of every
that's garbage.
shape.
I'm sorry, that's not garbage. I think it's garbage to memorize shapes of graphs when your calculator can do it. I know what you do. Yeah. Limison. It's an S, right? But okay, so we're gonna not do this first one, but we will do this second one here. Okay. Now you really, really want to use your calculator on this one, unless you memorize, like he was just talking about, what the shape of this is. It says it's a rose, but you still have to know where it intersects the graph, which I would not worry about it. Let's just graph it. Forget all this nonsense. This will help you greatly. So we're doing polar. Make sure the window goes from 0 to 2 pi. So this needs to be 2 pi here. It already is. I'm just writing it in there again for fun. Okay. Always go the full unit circle. It's just better. And let's put sine of 3 theta in there. And then we're going to graph it. And if you notice, it's 3 petal rows like it says. I'm going to actually zoom in, though. I think zoom trig zooms in. Nope, let's just do zoom in then. Zoom in. Ooh, look at that. It's amazing. All right, so all these petals are actually the same. I don't know why it looks like that. I think because my zoom settings are all weird. That's the baby. He needs to relax. Jeez. All right, going back to the graph. We just need to figure out the area of one of these. So in order to do that, what we can do is find the area of all of them and then just divide by 3. That's the easiest way to do it. Now, normally you'd have to memorize this, but what you can do is just go through the graph. So it starts there and make sure it goes around all 3 before you get to 2 pi.
Also, only finding one area for the.
Oh, shoot. Actually, hold on. Let's not do it that way. I just realized it only goes to pi, not 2 pi.
Yeah, because
This is why you have to graph it to figure it out. Okay, like the The 3 ends at, oh no, it does end at 2 pi. I lied. This one just said, hold on, give me 1 second. So there's 0, and it's drawing the, you just want to make sure you don't overlap for polar.
Okay.
It goes all the way around from here all the way to here. I believe that's pi over 6. Here, let's check it out. So I'm trying to figure out a way of getting it so people do not have to memorize all this. It's not pi over 6. That makes no sense. It's pi over 3. Okay. So we're going to go from 0 to pi over 3 for one of these. We don't need to worry about going to 0 to 2 pi. So we're just going from here, from 1 pedal, to pi over 3. So if you notice, that's kind of how it works here. 0, so from 0, and then just press left. Or I'm sorry, right. I'm going on my directions. And you want to go the entire way of that first pedal, and it goes to this right here, which is pi over 3. If you wanted, you can just keep going all the way around, and it goes to pi. So you can go to pi and then divide by 3. It doesn't really matter. Okay, whatever you want to do. Maybe pi divided by 3 is easier. It doesn't matter. Either way, let's set up this area. So we have the area going from 0 to pi over 3 of sine, oops, embarrassing, got the 1/2. 1/2 sine squared 3 theta d theta. Okay. Now, you can't do this antiderivative, so we're going to use this thing right here. Oops, that's embarrassing. Hold on, I was at the wrong layer on this. I didn't want to do that. There it is. Okay, cool. Cool. Let's do this. All right. So first thing we're going to do is replace this sine squared with this right here. So it's going to be the area is equal to 0 to pi over 3 of 1/2 times cosine. Now it's going to be 6 theta because it's 3 theta in here. So if it's regular theta, you just multiply it by 2, whatever's there. Minus 1 divided by -2, drop down the d theta. Okay, the rest of it, you should be able to do 0 issues. The area is equal to -1/4. I'm going to pull out the -1/4 here. And then we're integrating it from 0 to pi over 3 of cosine 6 theta minus 1 d theta. You should be able to do this antiderivative in your sleep. So it's going to be sine 6 theta over 6 minus theta. And we're integrating it from 0 to pi over 3. Okay, so you plug in the pi over 3 here. You end up with sine of 2 pi, which is 0. So it's going to be 0 minus theta minus, let's do this. I have to plug in 0. Sine of 0 is 0, so then minus another 0 is just 0. And you're left with positive pi over 12. Okay, use your calculator to test if this is right. Just throw this whole thing in your throw this whole thing in your calculator right here. Seeing if you get the same thing. So math 9, 0, it's pi over 3, whoops, 0.5 sine. It worked. It's a miracle. And that's the answer. How we doing?
That was fine for me.
All right, and then are we cool with these problems? Or these shouldn't be too difficult. Like I mean they're not easy, but like these are going to be on your quiz. They're going to be on your test. I just want to make sure everything's fair.
Do we have to know like the coordinates like from 0 to pi 3 to pi over 3 like by looking at a calculator?
Normally you would have to memorize those, but again, you can just use your calculator to find that.
Okay.
Yeah, this one was a little harder because it says 1 petal, so you have to know. Like the other one said 0 to 2 pi, so it was kind of easy for you.
So if it said 3 petals, you just times it by 3, right?
Yeah, if it was all 3 petals, yeah. Or you could just go to pi and it would be pi over 4. If you integrated from 0 to pi instead of 0 to pi over 3, it would do all 3 of them for you.
Oh, okay.
Yep.
Did the school ever get back to you on how quizzes were going to work with tests and midterms and whatnot?
I'm just going to do it that way.
Okay.
I try not to push things because it's like, well, I asked and nothing happened. So
Yeah.
yeah.
It's the same thing that happens when I email them.
Yeah, well, people are busy. I'm not trying to judge or anything like that, but no, yeah, I'm just gonna do it that way. There's some people, I mean, not like in math classes, but there's some classes where they just do a project. Kids cheat on the project the whole time and then get a grade for online stuff. So I'm okay with giving quizzes. The quizzes aren't easy. They're not a cakewalk. It's not like the average was an A. So hopefully they're not mad at me about it. I don't know.
Okay. And then same is the final grade just based off the same type of like problem grading, but just overall
Yes.
quizzes?
Yes. Yeah. So you'll have 6 quiz grades. So you'll have 6. Here, let's do this. You'll have
Oh, I thought it
6
was
quiz
8.
grades. Was it 8?
No,
No,
you're
because
probably
one of the weeks is a midterm and one of the weeks is
Yeah,
a final.
yeah. Okay.
So there's so then like you definitely have to have more A's than B's. I think this is going to be the minimum for an A. More A's than at least equal amounts of A's, and then you get one like freebie thing. Like normally to get an A, you have to have all A's and all B's, like an even amount.
Mm-hmm.
But I'm gonna have like one where you can do a little bit worse.
Okay.
So this would be the minimum for an A. I mean, if you average this out, it ends up being an A. I'm sure. I don't really know. So I'm sure people think it's unfair, but I round all the A's to A pluses too. So it definitely to your benefit.
Yeah.
Oh yeah. See, like this right here is an 88%, and I'm giving an A for it. So
Yeah.
Unless I added that wrong, but I just hate when people are like, "Oh, I was 1 point away from an A." It should be like, "Oh, I missed the understanding of one of the quizzes, not 1 point." Points just don't make sense. I mean, Lath, you know what I'm talking about because that's how I graded in high school.
It's a
I
very
don't know how I
good grade.
graded. Yeah, it's fair. It's how like normal people get graded on their work that they do. There's a rubric. Are you excellent? Are you average or whatever? It's not points.
Yeah.
Points are for the birds. But if your professor does do that, I'm not trying to diss those professors because I'm sure I'm gonna get in trouble for saying that. Everyone's different.
Buzzing sound is back.
Oh yeah, that happened last time. Here, hold on.
Bzz.
It's like bees have entered the chat.
Yeah. It was like a beehive attacked.
I don't know what it is. It keeps saying that my speakers and my microphone are blocked. I don't know what it is. So I ended up like
Really?
going on my laptop.
Did it go away?
Yeah, it
Yeah.
goes away.
All
You're
right.
good now.
It's weird. I have a really nice mic too, like a super nice mic.
What mic is it?
Blue Yeti?
No, I don't know what it is, but it was like an expensive one. It's a condenser mic.
Oh.
I bought a USB one. I used to have an adapter one. I did a Shure, what was it, a 57? Whatever the president uses, like whatever any president uses, not our president. I'm just saying like the one the presidents use was like a super nice one. But you had to have like an adapter to go to the computer. This one just goes straight USB. But if you like hear the audio in some of my videos, they're really good. If I do it on my iPad, it's terrible. But
I'm trying to get the Beats headset Bluetooth thing. Those look very nice. But
Yeah,
it's
but
very
dude, that's so much money.
I know,
can't
yeah.
justify spending money on that. I started using Adobe Premiere. Do you know what that is?
Yeah.
Mhm. Yeah.
Yeah, dude, it's awesome. Holy
Video
cow.
editing.
Yeah, for my videos. Yeah, instead of using iMovie,
Mhm.
using it's pretty awesome.
I mean, have you used After Effects?
I've seen it, yes.
Yeah, it's very crazy. That's like above Premiere.
Yeah, that's where it's like, why am I making this? Why would I make it that in depth when 100 people watch my videos? You know what I mean?
Yeah.
It's not even worth it. Like,
Just
those
make
are for people that have a full-time job and get actual like residuals.
Yeah.
But how do you know about the Adobe stuff? You took those classes?
No, I just work like randomly on them. I do like
Oh, dude,
you know,
that's the best. I'm telling you, when you're going to be an engineer too, like the more you know about other stuff, like just even to understand how the system works is amazing. Because you know what I mean. That's the thing. Some people look at it and go, all these buttons and all these words are just confusing. It's like, yeah, but like get past that and like make something with it. That's powerful.
I mean, it's just playing with it. It's just the idea.
Yeah, but people don't like doing that, dude. People, especially old people, they look at it and go, "Oh my gosh, this is too much." And I'm generalizing, not everybody's like that, but like some people don't like doing that. Here, I'm gonna stop the recording because I think we're done.
Yeah, before we get